Hello everyone, I welcome you all to this online classes. Today we are going to discuss about electric dipole and electric field due to a dipole. So here in the last section, in the last class, we discussed the electric field lines due to some charge configuration in which we consider electric dipole, where the electric field lines start from positive charge and end at negative charge. So we can able to generate these dipoles via the process of induction, charging by induction process. So first of all, what is meant by dipole, electric dipole? So here a pair of a pair of charges of equal magnitude opposite in polarity separated by a distance 2a is called an electric dipole. So here the line joining the two charges is called the dipole axis. So here the convention is that the direction of the dipole is from minus q to plus q2 charge. This is the convention followed for giving the direction of a dipole. And O is called the center of the dipole, which is the midpoint of the position coordinates of the pair of charges. So O is called the center of the dipole. Now let us consider what is the total charge on a dipole. So the total charge is nothing but minus q and plus q means that the total charge is 0. Is it if charge is 0, will it be the electric field 0? According to, we have a formula, electric field at a point P due to source charge Q is given by Q by 4 pi epsilon naught r square. So if Q is 0, total charge is 0, will the electric field, will it be 0? No, because this is not a point charge and these two pair of charges are not located at one particular point. They are at different points. So the total electric field due to minus q charge and plus q charge if added will give rise to the electric field which is a non-zero. The electric field has some net electric field. Suppose if you consider at different points, that is, let us say at a point P which is at a distance far from the distance between the pair of charges, that is for large distances such as r, the position vector or the point of concentration, where r is very much greater compared to the distance between the pair of charges. In that case, the electric field due to this pair of charges are equal in magnitude, opposite in direction, they cancel out. That we will see here. That we will observe in an example. Let us consider a pair of charges constituting a dipole. I consider a point P which is at the center of a dipole. So here, due to plus q charge, the test charge experiences strong repulsion, that is towards left side, and due to minus q, at the positive test charge at P will be attracted towards minus q. So here also the electric field due to minus q and the electric field due to plus q both are acting in the same direction. So the net electric field will be getting added up when the point P is in between the dipoles. Let us say the point P is away from the plus q charge. So in this case, the test charge experiences repulsion due to plus q. So it is acting in the right side, and the point P at which the test charge is placed due to minus q, it experiences attraction, so which is in the left side. So here these are acting in the opposite direction. So at one particular point, the electric field due to the plus q and minus q, they are equal and opposite, giving rise to the electric field approximately equal to 0. And here, for the case of a dipole, the electric field falls off faster than for a point charge. For a point charge, we know that the electric field is inversely proportional to the square of the distance. But for the case of a dipole, the electric field is somewhat different. that we are going to derive with the equation. What is the relation between the electric field and distance from the source to the point P? So will it be related like R square or something different, that we will see in the derivation part, right? So electric field due to dipole falls off in a somewhat different way, not like a point charge, right? So to calculate the electric field due to a dipole, so we have a pair of charges separated by some distance. So where we have to use the electric field due to a system of charges, what we have discussed. So if I have a n number of charges, I want to calculate the electric field at point P due to these charges. So what we have to do, let us consider charge 1 on point P and calculate the electric field at point P, and assuming 2 and 3 charges are absent. So similarly, the electric field at 2 is nothing but between 2 and point P, assuming 1 and 3 are absent. So E1, E2, E3, so on. So it is nothing but it's a combination of Coulomb's law and superposition principle. Similarly, here also, if I have two charges, a pair of charges which are separated by some distance, so we need to consider the electric field is nothing but the electric field due to plus Q charge and electric field due to minus Q charge, which is individually electric field we will get it from the Coulomb's law, and addition is nothing but the superposition principle. So here we will consider two simple cases. Suppose the arbitrary point P at which I want to calculate the electric field which is on the axis of a dipole. The first case is that the point P is on the axis of a dipole. Let us say these are the charges and point P is along the axis of a dipole or lying on the axis. And the second point, electric field for point P on the equatorial plane. So what is an equatorial plane? So suppose if you consider a plane which is perpendicular to the dipole axis, and passes through the center of a dipole. So if I have two charges, so let us say this is a plane which is perpendicular to the dipole axis and must pass through the center of a dipole. Is called equatorial plane, and P is nothing but the perpendicular bisector drawn onto the dipole axis. So at point P, what is the electric field due to this pair of charges we are going to calculate for us two cases. And we said that if I have two vectors which are acting at one particular point, so the resultant electric field we are going to determine using parallelogram law of vectors, right? By constructing a parallelogram, drawing a parallel vectors, the resultant electric field is given by the diagonal drawn to the parallelogram, right? So the first case is the electric field due to a dipole for a point which is on the axis of a dipole. So here this is a dipole, minus Q plus Q, and we said that what is the direction of a dipole? The direction of dipole is from minus Q to plus Q. So here it is pointing in the left side. Right. So we consider a point P on the axis which is at a distance R from the center of a dipole. So here what is the electric field due to plus Q charge at point P? So simply for a single charge, the electric field can be written as Q by 4 pi epsilon naught, the distance from source to the point P. In the same way, Q by 4 pi epsilon naught. So what is the distance from point P to plus Q? This is given by, so if this is total is R and this is A, so this will be R minus A is the distance from the plus Q charge to point P. And in which direction this force is acting? So here if I keep a test charge, this positive charge exert a repulsive force in the left side direction. So here this is the direction of the electric field due to plus Q charge at point P. Right. So the electric field at plus Q can be written as 1 by 4 pi epsilon naught q by r minus a whole square. What is p cap indicates? The direction of a dipole. Observe here, the electric field due to plus q charge and the direction of dipole both are in the same direction. That is why we have considered plus. Now, the electric field due to minus q charge at point P. So, what is the distance between minus q charge and and point P? So, which is nothing but r and a. So, r plus a. In which direction the test charge experiences force? So, if I have minus q, if I keep a test charge, this minus q attracts the test charge towards it. So, it is acting in the right side direction. Right, and distance is r plus a. So, we know that as r increases, electric field decreases. So, observe here, the arrow length for electric field due to plus q charge is more because the distance between this point plus q and point P is less. Whereas the electric field due to minus q is arrow length is small. Why? Because the distance is r plus a. So, as distance increases, electric field strength decreases. So, and also the electric field due to minus q charge is acting opposite to the direction of dipole. So, they are opposite. So, that is why we consider minus p cap. P cap means the unit vector for the direction of a dipole. So, this is the p bar is the direction of dipole and the unit vector along that direction is given by p cap. Right. Now, what is the total electric field? Which is nothing but the parallelogram law of vectors. Electric field due to plus q and electric field due to minus q. So, by adding this and the common things we kept outside, q by 4 pi epsilon naught, p cap is a common thing, and taking the LCM, r plus a whole square minus r minus a whole square by a plus b into a plus b whole square, a minus b whole square, a square minus b square whole square. And this is also a plus b whole square minus a minus b whole square, nothing but 4ab. So, 4ra into q. So, altogether 4qar by r square minus a square whole square into p cap. So, this is the electric field due to a dipole for a point P on the axis of a dipole. So, let us consider if the r, that is a point P, is at a large distances. So, if at larger distances such as r very much greater than the distance between the pair of charges, so a can be neglected in the denominator. So, r square whole square nothing but r power 4 and r get cancelled. So, we will get it as E bar is equals to 4qa by 4 pi epsilon naught r cube into p cap. So, this is the magnitude part and this is the direction part. And from this we can see electric field due to a dipole is inversely proportional to r cube. That is, the electric field falls off faster than a single pointer. For a single pointer, the electric field is directly inversely proportional to 1 by inversely proportional to r square for the case of a single charge, and for the case of a dipole, it is inversely proportional to r cube. So, the other case is for point P on the equatorial plane. So, equatorial plane is nothing but a plane perpendicular to the dipole axis and must pass through the center of a dipole. So, if we have a dipole, so this is nothing but a plane perpendicular to this dipole axis and must pass through the center of a dipole. Right. So, here we consider a point P lying in an equatorial plane. So, this is an equatorial plane. So, what is the electric field at point P due to this pair of charges? Due to this pair of charges. So, see here, if I keep a test charge at point P, which is at a distance r from the center of a dipole, r is the distance from the center to point P. And what is the direction of electric dipole? So, it is from minus q to plus q, nothing but it is in the left side direction. Now, because of the positive test charge, So what is the force exerted by the positive charge on the test charge? So it is a strong repulsion force. So the force experienced by the test charge is in this direction. So at point P, the electric field is in this direction, electric field due to plus Q charge. Let us consider theta is the angle made by this electric field with the dipole axis. So these are nothing but we can consider these two are parallel, and we call it as a dipole axis, right? So here theta is the angle made by the electric field due to plus Q charge with the dipole axis. Now what about minus Q charge? So here this minus Q charge attracts the positive test charge towards it. So this is the electric field at point P due to minus Q charge. So here at point P there are two vector tails. What are the vectors? Electric field due to plus Q charge and electric field due to minus Q charge. They are meeting at this point P. So due to these electric fields, what is the resultant electric field at point P? So for this we have constructed a parallelogram by drawing parallel vectors of E, electric field due to plus Q charge. This is electric field due to plus Q charge, and the electric field due to minus Q charge. And by drawing this, so the diagonal represents the resultant electric field due to these two pair of charges. So the resultant electric field is in the right side direction, and this resultant electric field is opposite to the direction of a dipole. So direction of dipole is in the left side direction, and the resultant electric field at point P due to this fields is along the dipole axis and acting in the right side direction. Right. Now here we can resolve this vector. If you have a vector A bar which is making an angle theta, we can resolve this vector into horizontal component and vertical component. Similarly, if I have a vector electric field due to plus Q charge which is making an angle theta, by resolving this into horizontal component is cos component and vertical component is sine component. Similarly, this vector electric field due to minus Q charge can be resolved into horizontal component minus Q cos theta and vertical component minus Q sin theta. So those are the electric fields. So now here electric field due to plus Q charge, the vertical component of the electric field due to plus Q, and the vertical electric field due to minus Q, they are in the same line but they are in the opposite direction. Now initially let us consider what is the magnitude of the electric field due to the pair of charges, right? So the electric field due to plus Q charge at point P. So what is point P? Which is at a distance. So if this is R and if this is half of the distance of dipole distance, so this will be nothing but from right angle triangle it is a square root of R square plus A square. So the electric field is given by 1 by 4 pi epsilon naught Q by R square plus A square. Here I am considering only magnitude, that's why I have not mentioned any direction part. So now what is the electric field due to minus Q charge at point P? Similarly, this minus Q charge and point P are also at the same distance of R square plus A square, because this is R and this is A. This will be R square plus A square, square root of. So by observing these two equations, the electric field due to plus Q and minus Q, they are equal in magnitude. Right. Now what we can see is vectors, direction part. So we got the magnitude part and now the direction part. So we said that the vertical components, nothing but the components which are perpendicular to the dipole axis. If this is a dipole axis, this component electric field due to plus Q, the vertical component, electric field due to minus Q, the vertical component, they are equal. Why? Because we said that the magnitudes are equal and these two vectors are acting in opposite direction. So plus 5 Newton and minus 5 Newton. So the resultant will become 0. Means that the components which are normal to the dipole axis. So these are the components which are normal to the dipole axis. They cancel out. Now what about the horizontal components? So the components which are lying, so this is a component along the axis of a dipole. And similarly, this E electric field due to minus Q, if you resolve, the horizontal component will become electric field due to minus Q cos theta. So they get added up. So the electric field components which are perpendicular to dipole axis cancel out, and the components which are lying along the axis, they get added up. And what is the resultant electric field? The resultant electric field at point P is the sum of the horizontal components. And in which direction it is? In a direction opposite to the direction of a dipole. So the total electric field at point P is given by electric field due to plus Q charge cos component, electric field due to minus Q multiplied by cos theta, and this resultant electric field is in a direction opposite to the direction of a dipole. E and P are opposite. So by writing the magnitudes of the electric field, so these two terms are same. And cos theta, what is cos theta? So because cos theta is common term, we kept outside, and from the figure we can see that cos theta is nothing but, so from the figure we can say that cos theta is adjacent side by hypotenuse. So what is adjacent side? Nothing but A by square root of r square plus a square. So cos theta, A by square root of r square plus a square. Now the total electric field is nothing but, so adding these two, 2q by 4 pi epsilon naught r square plus a square, and cos term is nothing but A by root of square root of r square plus a square minus p cap. So by rearranging we can write it as minus 2qa by r square plus 4 pi epsilon naught is there, 4 pi epsilon naught r square plus a square whole power 3 by 2 into p cap. Right. So for larger distances, the electric field can be written as minus 2qa by, so a can be neglected, r square whole power 3 by 2, so this will become r cube. Right. So here we can observe that the electric field will have a dependence both on the charge and distance between the pair of charges. So it's a dependence the electric field have a dependence both on charge and distance. So we have defined a new physical quantity called a dipole moment, which is nothing but one of the charge multiplied by distance between the charges. So one of the charges, if we have two dipole, one of the charge into distance between them. So this is the new definition of a dipole moment, and p cap is nothing but the indicating the unit vector along the axis of a dipole, along the direction of a dipole. We know that direction of dipole is from minus q to plus q. So now the electric field due to the electric field at point P on the equatorial plane, I am writing in terms of the dipole moment. So this can be written as, so q into 2m nothing but minus p by 4 pi epsilon naught r cube into p cap. So for the earlier case what we discussed, for a point P on the dipole axis, so it can be written as 2p by 4 pi epsilon naught r cube into p cap. Right. So here we can see that from the formulas of electric field at point P on the axis and on the equatorial plane, electric field due to dipole is inversely proportional to r cube. And also see here, let us assume only magnitude part. So this is magnitude p by 4 pi epsilon naught r cube, and it is 2p by 4 pi epsilon naught r cube. So the electric field due to dipole on the axis is more than the equatorial plane. It means that electric field not only depends on r, it also depends on the angle between r and p. See here, for a dipole, what is r? The distance from center to point P. And what is p? The direction from minus q to plus q. So observe here, the p and r, they both are parallel to each other for the first case. So it all depends on the angle between r and p, position vector and the dipole vector. And for the case of an equatorial plane, so what we have is, if we have a dipole with plus q and minus q, so here the dipole direction is from minus q to plus q, and point P, in which direction it is? R. It means that R bar and P bar are perpendicular to each other. Right. So for perpendicular, we got P by 4 pi epsilon not R cube. For parallel, if R and P are parallel, we got the electric field as 2P by 4 pi epsilon not R cube. So E has dependence both on the distance R and also on the angle between R and P. Right. So what is meant by a point dipole? Let us consider these two pair of charges minus q and plus q. They are very close to each other, means that the distance between them as 2a, which is tending towards 0. So in order to get a dipole of dipole moment is finite, what is the definition of dipole moment? One of the charge into distance of separation between the charges. So to see that this quantity to be finite, what we have to consider is the charge Q must be large. So such type of configuration we call it as a point dipole, where the two charges are very close to each other, giving rise to distance tending towards 0. In that case, the charge must be very large, forming a point dipole. So what are the electric field expression we derived for a point on the axis of a dipole and for point P on the equatorial? These equations are exactly true for the case of a point dipole. Right. And why we need to discuss about a dipole? What is its significance or importance? Right. Suppose if you consider some molecules in which the center of gravity of positive and the center of gravity of negative charge, they are coinciding because it is an atom. Molecule means it's a combination of an atoms, and inside an atom you have positive charge as well as negative charge. To see that, the atom should be a neutral. So here for a molecule, let us say this is a molecule in which the center of gravity of positive and center of gravity of negative charge, they are coinciding. So in that case, there is no dipoles present. What is meant by dipole? Two equal and opposite charges separated by some distance, then we have a dipole. So we don't have any dipoles. So such molecules we call it as non-polar molecules. The examples for it is CH4, carbon dioxide, in which the molecules, the center of gravity of positive and negative charge coinciding. So they don't have any dipoles, no dipoles. So how we can get dipoles? So here, by applying an external field, let us say if you bring a negative charge, a plastic rod, so here then positive charge is getting attracted by the negative and negative charge getting repelled by the negative charge. So due to which there will be a small distortion. So these are the spherical structure. So the negative and positive charge are slightly displaced, giving rise to a dipoles, and such dipoles we call it as induced. The dipoles are induced with an external field E. So dipole induced with the applied electric field. So such a type of molecules we call it as non-polar molecules. Right. So what is meant by polar molecule? In those molecules, the center of gravity of positive and the center of gravity of negative, they are separated by some distance. Means that we have a dipoles even in the absence of electric field. We are not applied any electric field. Still, the charges are separated by some distance, having net dipole moment. So now we are going to discuss about if a dipole having net dipole moment P kept in a uniform electric field. So first of all, we are going to know about what is uniform electric field. So see here, this is a uniform electric field. At each and every point, the electric field is same because electric field is a vector. So both the magnitude and direction is same at each and every point. Suppose if you consider a parallel plate capacitor. A parallel plate capacitor means two metal plates which are charged positive and negative. So in between the parallel plates, the electric field vector which is pointing in the downward direction, so whose magnitude and direction remains same. This is called uniform electric field. At each and every point, both the magnitude and direction of the electric field remains same. So a parallel plate capacitor is the best example for creating a uniform electric field. And non-uniform electric field. So the electric field changes from point to point either in magnitude or direction or both the magnitude and direction. So that is called non-uniform electric field. Suppose if you consider a point charge, we know that the electric field due to point charge is inversely proportional to square of the distance. So here at this location the electric field is strong. As we move away, the electric field goes on decreasing. So on one particular field line, the electric field magnitude goes on decreasing. So at different points, both the magnitude and direction of the electric field changes. So this indicates a non-uniform electric field. Non-uniform electric field. Now we consider a dipole which is kept in a uniform electric field. So what happens? What are the forces experienced by a dipole kept in a uniform electric field? Remember that already we have a net dipole and that is kept in an electric field, right? So here let P be the dipole of dipole moment P. So P indicates the dipole moment and which is kept in a uniform electric field E, which is pointing in the upward direction. And theta be the angle between P bar and E bar. So what is P bar? So if this is a dipole, the direction from minus Q to plus Q is called the direction of a dipole and the electric field is pointing in the upward direction. So angle between P and E is called theta. Right. So if you keep this dipole, what happens? So let us say this is a minus Q charge and this is plus Q charge. So because of this charge kept in an electric field, what is the force? What is the force experienced by plus Q charge given by QE from the definition? E is nothing but force per unit charge, or the force experienced by the positive charge, it's not test charge, it is plus Q charge kept in a uniform electric field, it experiences a force in the upward direction. Why? Because Q is positive, the force experienced is also parallel to the electric field. Now in the same way, the force experienced by the minus Q charge kept in a uniform electric field. So the force will nothing but minus QE. Here the charge polarity is minus Q. So due to which the force experienced by the minus Q charge is in the downward direction. So now these are the two pair of forces equal in magnitude. Both magnitude both are QE. Equal in magnitude but opposite in direction. So what is the net force acting in a dipole? The net force is nothing but force acting on plus Q charge and force acting on minus Q charge. So the net force is 0. If net force is 0 means that there is no translatory motion. The dipole remains there itself. But these pair of forces which are acting at two different positions, so constitute a torque or couple. So this pair of forces are trying to turn the dipole in the direction of the field, nothing but the torque. So due to a pair of forces, there is a torque. Torque is trying to turn the dipole in the direction of the electric field. Now, what is the magnitude of the torque? So we know that torque is nothing but one of the force into perpendicular distance between this pair of forces. So this is one pair of, this is a force acting on plus Q and force acting on minus Q. So what is the perpendicular distance? So this is the perpendicular distance. So here we have drawn. So these are the lines in which the forces are acting, and this gives rise to the perpendicular distance between pair of forces. So nothing but AC. Right. So one of the force is magnitude of the force, because we are considering magnitude. So one of the force is QE into the perpendicular distance between the pair of forces is AC. Right. So we said that the angle between E and P is theta. So here also E and P, it is theta. And what is the remaining? If this is theta, total is 90. So this remaining will become 90 minus theta. And we constructed a right angle, perpendicular distance. So this is 90. So this is 90 minus theta, 90. So the remaining angle will be 90. To see that the total angle is 180. So from the figure, what is sine theta? So if this is theta, the opposite side by hypotenuse. So what is opposite side? AC by AB, or AC is nothing but 2A sine theta. What is AC? Perpendicular distance. So QE into 2A sine theta. So here by writing this 2QA into E sine theta. What is 2QA? Nothing but one of the charge into separation between charges, which is a dipole moment. So P E sine theta. So we can write this in vector form as tau bar. Till now we have discussed about the magnitude. So the direction of the torque is given by writing this as P bar cross E bar. That is the vector product of the dipole moment and the electric field. So here, because of these two pair of forces acting in two different positions, the torque is trying to align the dipole in the direction of the field. So if I have P and if I have E, so P bar cross E bar, so the thumb indicates the direction of the torque. So it is pointing out of the paper. So P bar cross E bar. So here this dipole is trying to align in the direction of the electric field because of the torque. This torque is trying to align this dipole in the direction of the electric field. So once if the dipole is rotated in the direction of the electric field, then what will be the theta? So theta will become 0. Suppose if this is electric field and the dipole is also aligned, both are parallel. Who are doing this part? The torque is trying to align the dipole in the direction of the electric field. Once they are aligned in one direction, theta will become 0. So if theta is 0, torque will become 0. Only this torque is trying to align the dipole in the direction of the field. Once if it is aligned in the direction of field, the torque will become 0. So the alignment of the dipole will be due to pair of forces, and this pair of forces constitute a couple or torque, and this torque is trying to turn the dipole in the direction of the electric field. So the vector products the direction of the torque is given by P bar cross E bar. In which direction the torque is acting? The torque is acting P bar cross B bar, curling your finger from P to E. So the thumb indicates the direction of the torque, nothing but it is acting out of the paper. So if a dipole kept in a uniform electric field, we observe the dipole is trying to align in the direction of electric field. Right. Suppose if a dipole is kept in a non-uniform electric field, Let us say, so here this is indicating the electric field pointing in the upward direction, and this arrow indicates the magnitude of the electric field goes on increasing from point to point. So it's a representation of the increasing electric field. So if we have an increasing electric field, and a dipole is kept in this increasing electric field. So the force experienced by the minus q charge, this is nothing but minus q into, let us say at this point the electric field magnitude I am considering it as 10 units. The formula is QE, and here E is not a constant because it is a non-uniform electric field. I am assuming that this arrow indicates the increasing electric field, means that the magnitude of the electric field goes on increasing. So at the location of minus q, let us say the magnitude of the electric field I am observing it as 10 units. And at plus q charge, that is at this point, so it goes on increasing. Let us say the field at this plus q charge, I mean assuming it as 30 units. So we can observe here the net forces. So the force acting on minus q and the force acting on plus q, they are opposite in direction. Yes, they are in opposite in direction, but the magnitudes are not equal. In the earlier case we have seen these are two pair of equal forces and equal in magnitude, opposite in direction. But here in a non-uniform field, yes, these are the forces which are acting in opposite direction and their magnitudes are not equal. So in that case we can expect a net force acting on a dipole. So if there is a net force, there is a translatory motion. It means the dipole can able to move in the field. And again we have a pair of forces acting at two different positions constitute a torque. So here in this example, if we have a non-uniform electric field and electric dipole is kept in a non-uniform field, the dipole experiences translatory motion as well as the torque, nothing but the turning or rotatory motion. So this is a complex way to understand. So let us consider a simple case. Yes, we have a non-uniform electric field, but E, the electric field and the dipole, the direction of a dipole, if they are parallel to each other. We are not going to discuss this one. We are going to discuss a simple case where electric field and direction of dipole parallel or anti-parallel to each other. But remember, the electric field is not a uniform. It is a non-uniform electric field. For simple cases, let us say E and P are parallel to each other. So this is the direction of the electric field. So assume that it is an increasing electric field. In what way it is increasing? The magnitude of the electric field changes from point to point. So it's a non-uniform electric field. So the magnitude of electric field goes on increasing. Now I have a dipole. So what is the direction of dipole? From minus q to plus q. So the applied electric field and the direction of dipole both are parallel to each other. Right. So what is the force experienced by minus q charge? So the force experienced by minus q charge is due to the electric field. So what it will do? It tries to, so force is nothing but q times of E. So if the electric field is in this direction, so minus QE. So this is the force experienced by the minus q charge due to this electric field. And what is the force experienced by plus q charge due to electric field? See, here the magnitude is more. Let us say, if I consider different divisions, this is 10, this is 20, this is 30, this is 40, this is 50. Likewise, so here 10 units of electric field is acting on minus q charge, right? So giving rise to the the force is minus, the force acting on minus q in the left side direction. Now here at this point, the electric field strength goes on increasing. Let us say it is 70. Now what is the force on plus q charge? The force acting on plus q charge. So here the test charge experienced strong repulsion due to this plus q. So here this is the force acting on plus q in the right side direction. Observe this arrow length. Here I have given the arrow length is large. Why? Because at this point, even though the charges are same, but the electric field here is more. If the electric field here is more, so the force is also more. Whereas here the electric field magnitude is less, so the force is also less. So what is the resultant due to these forces? In which direction? So this is let us say 10 newtons in the left side, and let us say this is 15 newtons in the right side. So what is the net? Will be 14 newtons acting in the right direction. So this is the net force. So the net force and the electric field both are parallel. What is electric field? Pointing in the right direction, and the net force is also pointing in the right direction. So this in this case, if E and P are parallel, electric field and the dipole both are parallel to each other, their forces are in such a way that the force on plus q charge is more than the force on minus q. So the net force is pointing in the direction of the electric field. So both E and Fn are in the same direction. Now, if E and P are anti-parallel to each other, so see here, this is the same thing, increasing electric field whose magnitude goes on increasing, and dipole, see, minus q plus q. So here E and P are anti-parallel to each other, right? Now, what is the force experienced by plus q due to electric field? So here, this plus q charge and the magnitude of the electric field goes on increasing. So because if I have electric field, this my plus q charge exert a repulsion. So this is the force at plus q charge. And here minus q charge, because of the electric field, it attracts. So here the force is larger in magnitude. Why? Because here the electric field is large. The same example, the same thing. So minus q times of 10 or plus q times of 30. The same thing we have to remember. So here the force experienced by minus q is this much, because the electric field strength is large, but it is pointing in the opposite direction. F equal to EQ, here minus E, minus charge, that is F and E both are opposite, whereas here plus q charge, so both electric field and force are acting in the same direction. So what is the net force? So this is left side magnitude is more and right side magnitude is less, so the net is acting in the left side direction. So here the net force and the increasing electric field, they are anti-parallel to each other. E and Fn are anti-parallel to each other. So for the case of if E and P are parallel, the net force is in the direction of the electric field. If the E and P are anti-parallel, the net force is opposite to the electric field, right? So by considering these things, we are going to apply for a simple example. In the starting of the chapter, we said that if you comb your hair, dry hair, the comb is getting a charge like negative charge, and if you bring small pieces of paper, the pieces of papers are getting attracted by the comb, getting attracted by the comb. So here, that example we are going to discuss with the dipole concept. So here the comb which is getting a negative charge, and this is also creates electric field which is non-uniform electric field, that we need to remember, non-uniform electric field. So this is indicating the direction of the electric field. So from point to point, the electric field magnitude is increasing. So if you keep papers which are insulating substances, if you are kept in close to the charged body, negatively charged body, this there will be charges developed, induced because of the minus charge. If we have minus charge, initially the bits of papers is having neutral. Now once if you keep the bit of paper close to the charged body, so here the negative charge is repelled by the charge on the comb and positive charge attracted. So dipoles are induced. So what is the direction of the dipole? The direction of dipole is from minus to plus. So it is in the direction. So observe, what is E and P? Both are parallel to each other. The electric field due to charge on the comb and the dipoles induced in the bits of paper both are parallel, and this is a non-uniform electric field. The electric field around a body is non-uniform. In that case, if E and P are parallel to each other, what is the net force acting on the body, charged body? The net force is in the direction of the electric field. So what is the direction? This is the direction. So the net force, so these bits of paper experience a force in the direction of the electric field. So the papers is getting attracted due to a non-uniform electric field. The net force acts, and because of the net force, this bits of paper, there will be charges induced. So it becomes a dipole, and the direction of the dipole and the electric field both are parallel to each other, due to which the net force experienced by the bits of paper is along the field, means that these are attracted towards the comb. That is the reason for why bits of paper attracts the charged body, because E and P are parallel. E and P are parallel. So if E and P are parallel, the net force experienced by the piece of papers is along the electric field, that is towards the comb. Thank you.